Hi everyone, we're starting Chapter 10, which is about bonding, and we'll learn how to draw bonds between atoms. The very interesting application of drug design is the beginning of the chapter, and we have this image of the HIV protease and the drug indinavir, which was designed to inhibit its action, which is to allow HIV to replicate itself. So that's a really important drug that's allowed AIDS patients to have 10 and 20-year lifespan after diagnosis. I have a really interesting clip from TED Talks that we'll listen to before we go on, just to kind of bring us up to date with where that HIV vaccine is. I think you'll enjoy this.
A vaccine trains the body in advance how to recognize and neutralize a specific invader. After HIV penetrates the body's mucosal barriers, it infects immune cells to replicate. The invader draws the attention of the immune system's frontline troops. Dendritic cells, or macrophages, capture the virus and display pieces of it. Memory cells generated by the HIV vaccine are activated when they learn HIV is present from the frontline troops. These memory cells immediately deploy the exact weapons needed. Memory B cells turn into plasma cells, which produce wave after wave of the specific antibodies that latch on to HIV to prevent it from infecting cells, while squadrons of killer T cells seek out and destroy cells that are already HIV infected. The virus is defeated. Without a vaccine, these responses would have taken more than a week. By that time, the battle against HIV would already have been lost.
Drug design has got to be one of the most challenging and rewarding careers you could possibly have, and it's taken on such an international aspect. We keep more open books on research findings to facilitate quick drug design. It's to all of humanity's benefit that we resolve issues such as HIV, because all great drug design chemists first learned Lewis theory, which is how we figure out how the atoms can be bonded together to form the shapes we want. So, starting at the beginning, Gordon Lewis is an American chemist who developed this method, and it works really well for us. We learn how to draw atoms with just their valence electrons showing, and then we put them together and form molecules. And I believe you have done this in 8th grade to some extent, and we're just going to extend that further. So we're going to learn how to do Lewis dot structures. First of all, let's review. Last chapter we were doing our electron configurations. So for oxygen, the electron configuration would be 1s2, 2s2, 2p4. And if we ask how many valence electrons there are, we'd look at the highest energy level ever achieved, and that was energy level 2. And there are 6 electrons, 2 there and 4 here, for a total of 6 electrons in the valence shell. We draw a Lewis structure of an oxygen symbol with 6 electrons around it, and we usually do it as 4 pairs, okay, like a 4-sided thing, and that is oxygen showing its valence electrons. We also remember you can always tell the valence electron count on an atom by its column number on the periodic table. So if we go across the second row, we would have this series of Lewis structures for all the atoms as we increase valence count as we go along. And right here I'd like to make a comment, because we have the transition metals that show up right in here, and we say all of those have 2 valence electrons unless otherwise memorized or noted. So we say atoms become more stable if they achieve the octet, with the exception of hydrogen and helium, which are happy with a duet of 2. So we have 2 main bond types that we're going to draw Lewis structures for. It's the ionic bond and the covalent bond. We say the ionic bond forms between a metal and a nonmetal, and it involves the transfer of electrons from the metal to the nonmetal. The covalent bond is between 2 nonmetals and involves sharing. So let's look at ionic compounds and how octets are achieved. If we have potassium with chlorine, we have a metal and a nonmetal, and we would see chlorine as the more electronegative atom that will take the electron away from potassium. We show potassium transferring it to chlorine, and chlorine sitting with a full octet with a -1 charge as a result of having an extra electron. And then potassium, we don't show its underlying electrons, and we show it as just a barren cation. That's the Lewis dot structure for potassium chloride. Here's a similar one for magnesium oxide. We see magnesium with 2 valence electrons, but to become stable and reach an octet. But to be stable, magnesium would shed its third shell and go back to a full octet as 2s2 2p6, and existing as cation Mg2+, it's more stable, and oxygen achieves the octet by picking up magnesium's 2 electrons and exists in a more stable way as O2-. Try this. Try writing sodium sulfide as a Lewis dot structure and aluminum chloride. Pause this and make your attempt, and then we'll check it. So hopefully this is what you did. You showed sodium with 1 electron and sulfur with 6. Now you could show 3 pairs, but this kind of sets us up to show the obvious. We could now put another sodium here because we see that 1 sodium won't meet the need of the sulfur. And then this electron will get transferred here, leaving us with Na+, Na+, and sulfur with an octet, minus. That would be the correct way to show the Lewis structure. We use brackets when we carry charges. Alright, let's do the same for aluminum. Aluminum has 3 valence electrons. So we have chlorine, which is 1 short. So, as you've probably figured out, 3 chlorines would love to partner up with this aluminum and take its 1 electron. So let me put the other 3rd chlorine up here. And then we could show the transfer to these 3 chlorines. And you would be left with a 3+ aluminum and 3 chloride ions. Three of those guys. Let's move on to covalent compounds. As you recall, covalent compounds, nonmetal, their orbitals overlap and they share electrons. Because nonmetals are medium in electronegativity, they're adaptable and they do whatever's necessary for the atoms that they bond with. And the classic here are hydrocarbons. Carbon is wonderful at forming long chains. There are an infinite number of carbon compounds. And so a key thing we'll look at now are the covalent compounds of carbon. Underneath carbon on the periodic table, you've got silicon. So silicon does all the same things that carbon does. So let's get into the habits of writing covalent compounds using Lewis methods. So here we have a hydrogen with its single electron and the oxygen with its 6. We could draw water, which is non-metal, and hydrogen can be considered a metal or a non-metal. We're going to consider it a non-metal right now. This is a covalent compound where the hydrogens come in and share their electron. They don't transfer it to the oxygen. They share it, and it exists as a molecule. Octet here on oxygen, and the hydrogens are complete with their duets, making all atoms stable in this configuration. The Lewis theory explains why the halogens exist as diatomic molecules. You see here a single atom of chlorine, but if it would couple up with another chlorine atom, they can share and each have an octet. All the halogens do this. So does hydrogen. Hydrogen's complete with a duet, 2 hydrogens together, so we see H2 molecule in nature. What do we do with something like oxygen? We memorize that oxygen is also a diatomic molecule. But if I only have 6 electrons, if I put 2 oxygens together, I am not able to get an octet around this oxygen. Well, now we see the appearance of double bonds. In the Lewis method, you can show, once you run into this situation of short on one of them, we can move this electron pair right here. This electron pair can move in and form a double bond between these two oxygen. This line method, each line represents 2 electrons, so these are equivalent representations right here. In this way, we see this oxygen as having an octet, and so does this oxygen have an octet. Okay, so this is stable for the oxygens. Here's a triple bond example. Nitrogen gas is super stable. Triple bonds are hard to break. They are stronger than double bonds, which are stronger than single bonds. Well, with nitrogen, when you only have 5, the first bond they form leaves them each with an apparent 6. But again, we can take this pair and move it in and form a double bond here, and again to form 3 bond pairs shared between the atoms, and we have the formation of a triple bond. This slide is good for showing the bond length differences between the single, double, and triple bonds. Here you have a carbon. The carbon is the black and the hydrogen is the white. And we have a single bond here with a length of 153 picometers. Picos 10 to the minus 12 meters. Here we have a double bonded carbon double bond, and it has a length of 134 picometers, and the triple bond is 120 picometers. Besides shortening, you also have a loss of flexibility as we form double and triple bonds. It becomes rigid and very electron rich, and those factors become important in determining where there are electron-rich regions in a molecule. Let's now create some molecular structures using the Lewis method. We'll do methane first. It's CH4. The first decision you have to make is which atom do you put in the middle. I've got 4 hydrogens and 1 carbon. Get used to the idea that carbon loves to be in the center. And carbon has 4 electrons, and we draw them as such, 1 on each side. And I think you could see how the hydrogens would just perfectly complement carbon here. If they would all share their 1 and overlap their orbitals, you've got the 1s orbital of hydrogen overlapping with, it's a blended thing that happens with carbon where it's 2s and 2p's hybridize and form these sp3 orbitals, but we get this structure for methane. Now let's draw the structure for carbon dioxide. Once again, carbon loves to be in the center, so we draw it with its 4 valence electrons, and now we'll show oxygen coming in with 6. 1. Do the first one always in the sharing mode. That's the point. They want to overlap and share to get the octet. Oxygen comes in with 6, and here's the other oxygen. 1, 2, 3, 4, 5, 6. Okay, now we have this, we are short on the octet. We have 7 and 7 and 6. This is the setup for multiple bonds forming. So this single and this single will merge to form a double bond here, and this single will feed in to form a double bond there, and the net of all of that is carbon dioxide. It has a central carbon with double bonds on either side, and each of the end oxygens have 2 lone pairs of electrons.